All right, hello everyone, and welcome to our lesson on 5.7 and 5.8, which has to do with reaction mechanisms. Today we are going to continue learning that many reactions don't happen in one step. They're going to occur through a bunch of elementary steps known as a reaction mechanism. When all the steps are added together, they should match the overall balance equation. And mechanisms can include reactants, products, intermediates, and catalysts, and you should be able to identify all of those components by the end of this lesson. A reaction mechanism explains how a reaction happens, not just the final net equation. It breaks the overall reaction into a series of elementary steps that take reactants to products. In this example on the right here, we see that the reaction occurs in two elementary steps, and the slowest step is the rate determining step, meaning it controls the overall reaction rate. Any species that is produced in one step and consumed in another, like NO3 here, is called a reaction intermediate because it appears in the mechanism, but it cancels out and does not appear in the overall balanced reaction. A reaction mechanism breaks one overall chemical reaction into those elementary steps that show what's happening at the molecular level. In this example, the decomposition of hydrogen peroxide happens in two steps, and when you add those steps together, you get the overall reaction. 2H2O2 reacts to form 2H2O plus O2. In 5.4, we learned about intermediates. Remember, an intermediate is something that is created and consumed in the same mechanism. So here we can see in our first elementary step, iodate or IO negative is created, but in the second elementary step, iodate is going to be used up. So when we create our final net reaction, iodate is not in that reaction because it cancels out in both sides. When we look at the overall balance equation, notice that iodate and iodide, which is IO negative and I negative, do not appear in the final reaction. That is going to tell us that they are not part of the net change. They're just involved in the pathway the reaction takes. So elementary steps show us what happens at the molecular level, so they can include special species like intermediates and catalysts that cancel out when the steps are added together. In this mechanism, we can see that iodate or IO negative is the intermediate because it's made up in step 1 and then used in step 2. And we can also see that we have a catalyst here because we have something that is introduced at the start of the reaction and comes out the same exact way. And remembering back to 5.1, we talked about catalysts, and we know that catalysts are regenerated, meaning they're not actually consumed. They're just going to lower the activation energy and lower the rate in turn. So by looking at this mechanism, you should be able to identify that iodate is our intermediate and iodide is the catalyst. All right, let's look at this reaction mechanism with 3 elementary steps. First, it asks you to identify the intermediates in the mechanism. Remember, intermediates are going to be produced in one step and then used up in another step. Now, I can already kind of tell from step 1 and step 2 that we have HCOOH2 plus that is both created and consumed in 2 steps. So when we go to write our equation, these are going to cancel each other out. So that is by definition an intermediate. And then you can also see that HSO4 minus is going to be created in step 1 and used up in step 3, and they are nowhere else in the 3 elementary steps. So we know when we write our overall equation, those are going to cancel each other out. So those are also an intermediate. Next, it wants to identify the catalyst. Remember, a catalyst is something we introduce to the reaction. It's going to lower the activation energy, which makes the reaction go faster. And then it's going to come out the exact same way. So you're looking for something in the reactants of step 1 that's also in the products of the final step. So here you can see that that is going to be sulfuric acid, or H2SO4, and that will not be in the final overall chemical equation because it exists on both sides and there's only one of them, so those cancel out fully. So that would be our catalyst. All right, and while I was writing down that catalyst, I noticed another intermediate that we forgot. So if you caught that before I did, great job. But HCO plus is also something that is created in step 2 and used up in step 3, and there's only one of those, so those cancel each other out, which means that is also an intermediate. Now, because we already canceled everything out, it's very easy to write our overall chemical equation. And we can see that this is a decomposition reaction of HCOOH, and that is going to form CO, or carbon monoxide, and water. So let's review how a reaction mechanism is made of multiple elementary steps and how the rate determining step controls the overall reaction rate. In step 1 of the diagram, the reactant particles must undergo a collision with the correct orientation and enough energy to overcome that activation energy. But because this step is labeled as slow, it's going to have the smallest rate constant K and produce the intermediate and product of that step at a really slow pace. In step 2, the reaction proceeds rapidly once those species come from step 1 and are available to react. So this step has a larger K and does not limit the overall rate. So since the overall reaction rate depends on the frequency of successful collisions in the slowest step, step 1 is going to determine the reaction speed, even though step 2 occurs quickly afterward. Now, just for a quick practice, go ahead and pause this video and identify the intermediate. And if you identified ClO, that is correct. That is our intermediate for this reaction. And now go ahead and pause the video and identify the catalyst. And if you selected this one, you would be correct. All right, so here we have a 3-step mechanism. It first wants us to identify the intermediate. So looking at step 1, I can see that I create this molecule and then I consume it in the next reaction, and it does not appear anywhere else. So that would be one of my intermediates. And then I can also see in step 2 that this molecule was created and then it was consumed in step 3, and I see it nowhere else in the mechanism, so that is also an intermediate here. Now it wants us to identify a catalyst. Remember, a catalyst is going to go in as a reactant in step 1 and come out the exact same way as a product in the final step. And as you can see here, there are no molecules that do that. We have different molecules in the reactant side of step 1 and the product side of step 3. So there are no catalysts in this reaction. And now let's get our overall chemical equation. We already canceled out our intermediates, so this should be quite simple. We have NO, and we have 2 of them in our very beginning of the mechanism. So we're going to have 2 NO. Then we also have 2 O2s. And then our products are 1 N2 and 2 H2Os. That would be our overall chemical equation for this mechanism. All right, for this example, it says the decomposition of ozone in the upper atmosphere is represented by the equation below. O3 plus O reacts to form 2O2. Below, we are given a potential energy diagram with the decomposition of ozone in the presence and the absence of NO. And we can see from the key, our solid line is going to be in the absence of NO, and our dotted line is going to be in the presence of NO. Now we can see with our dotted line in the presence of NO, we have a lower activation energy, which is giving us the idea that NO is going to be our catalyst. And when we introduce that catalyst, we're going to have a new mechanism where we have a certain number of elementary steps. So what would you look for in identifying the reaction mechanism associated with this potential energy diagram for the catalyzed reaction? Now, in the curriculum, you don't actually have to look at one of these and give me the mechanism. You just have to be able to identify what would be a correct mechanism from a list of choices. So for this slide, I just want to talk about what would you look for. So first thing I want you to notice is that we have two peaks. And when we have two peaks in a PE diagram, that's going to signify that we have two elementary steps in the mechanism. The next thing I want you to notice is that our first elementary step is going to have a much larger activation energy than our second elementary step, which means our first elementary step is going to be our slow reaction or the rate determining step. And then finally, because we can assume that NO is our catalyst, we need to look for a mechanism that shows NO as a reactant in step 1 and as a product in step 2. And knowing those three things is going to help you easily to identify which of the mechanisms are correct for this reaction. All right, it says the following equation represents the decomposition of N2O5, for which the rate law is rate equals K times the concentration of N2O5. The following mechanism is proposed for the decomposition of N2O5. Identify which step of the proposed mechanism is the rate determining step and justify your answers in terms of the rate law given. So we know that this is our rate law up here, and we also know that our rate determining step is only going to have one N2O5 as the reactant, and that's it, because if it had anything else, then it would be in the rate law. So because we know that, that means step 1 has to be our rate determining step because it only has one N2O5 molecule as the reactant. And here is what I would write on an FRQ. All right, and now let's move into 5.8, which is on reaction mechanism and rate law. So reaction mechanisms explain how a reaction happens by breaking it into elementary steps, which I know you have heard me say multiple times at this point. We know that the slowest step is the rate determining step, and it's going to control the overall reaction speed. So the rate law is based on the reactants in that slow step. As we continue learning, we'll use mechanisms to predict rate laws and identify which step must be the rate determining step. In this reaction, we're tracking how the concentration of NO2 changes over time to figure out the reaction order. So when we graph concentration of NO2 versus time, you can see that the data is curved. So it is not going to be our zero order because plain concentration versus time is not going to be linear. Then moving on to the natural log of the concentration of NO2, we can still see a curve here, which means it is also not first order. Now remember, AP Chemistry is only going to be testing you with these specific concentration versus time graphs for only 0, first, and second order. So if it's not 0 or first, you can assume it's second. But just in case you didn't want to do it that way, you can see that when we have the inverse of concentration of NO2, we do have our nice linear regression here. So it's going to be second order. Now that we know we are just looking at NO2 and we know that it's second order, we can go ahead and write the rate law. Whenever it asks you to write rate law, remember we're starting with the word rate. So it'll be rate equals K times the concentration of NO2. And because we know it's second order, it will be raised to the second power. Part 3 of this example says, using the mechanism for the reaction above, is the rate law described by mechanism 1 shown consistent with the rate law you wrote in question number 2? Justify your answer. So remember, for our rate law that we wrote, it was rate equals K times the concentration of NO2 squared. And so now let's compare that to this mechanism using what we've already talked about in terms of the rate determining step and how that works for rate. So when we are given a mechanism, we look at which step is our rate determining step, and that is going to tell us how to write our rate law. So when the first step is our rate determining step, it's nice and simple. You're just going to write rate equals K times your concentration raised to the power of how many you have. So here we have 2 NO2 molecules, and that's it. So it's going to be concentration of NO2, and because we have 2 of them, it's going to be raised to the second power, which is exactly the same as the rate law we wrote on the previous slide, just using concentration versus time. Now, to be successful in Unit 5, you have to be able to identify reaction mechanisms from rate law, and you also have to be able to identify rate law from reaction mechanisms. So I went ahead and wrote out all the steps for you. So if you wanted to pause this and take notes, I think they could be helpful if you weren't understanding all the little details that we've been doing so far. All right, this example says a reaction and its experimentally determined rate law are represented above. A chemist proposes 2 different possible mechanisms for the reaction, which are given below. So when we're given both the overall equation and the rate, you have to make sure your mechanisms first follow the rate and also cancel out all intermediates to get your final overall equation. So first, let's focus on rate and make sure both of the mechanisms follow that rate law. And with this rate law, we know we're only going to have one X2 molecule as a reactant in the rate determining step, or else this would not be the produced rate law. So in mechanism 1, our first elementary step is the rate determining step, and we only have one reactant in one of those X2 molecules. So our rate is going to be equal to K times the concentration of X2 raised to the first power, because we only have one of them, and that is consistent with our rate law. Now let's do the same with mechanism 2. Again, the first elementary step is our rate determining step, and we only have one X2 molecule, so it will be rate equals K times the concentration of X2 raised to the first power, which also is the same and consistent with our given rate law. So now we have to make sure that everything cancels out in these mechanisms to give our overall reaction, which is X2 plus Y2 forms X2Y2. So for me, the easiest way to do this is to cancel things out and see what I'm left with. So let's start with mechanism 1. We have 2 X's on the product side and 2 X's on the reactant side, so those are gone. We have XY2 as a product in step 2 and XY2 as a reactant in step 3. And all we are left with is 2 reactants, X2 and Y2, and 1 product, X2Y2. So mechanism 1 is consistent with the reaction. And now let's do the same for mechanism 2. We can see that 2X were created in step 1, and 1X was consumed in step 2, and 1X was consumed in step 3, so those are canceled out. We can also see that XY was an intermediate formed in step 2 and used in step 3, and we have another intermediate Y that was formed in step 2 and consumed in step 4, and then our last intermediate was produced in step 3 and consumed in step 4. And again, we have X2 and Y2 left as our reactants and X2, Y2 as our products. So that also follows our overall reaction, which means both of these mechanisms follow the reaction and the rate law, which means they are both consistent with what we are provided. All right, and then to wrap up our video, we're going to end it on an example problem. It says the rate law for the reaction represented by the following equation is rate equals K times the concentration of NO2 squared. Which of the following mechanisms is consistent with the rate law? So remember, when we're looking at this rate, we know that we only have NO2, and we know that we have two of them if we're looking at a mechanism. So the first thing you need to do is realize that you have to find your slow rate determining step, and it can only have two NO2 molecules. It can't have anything else, or else it would not be that rate.